Hello students, so welcome to this lecture on exploring the delay of the NAND and the NOR gates. Um, so let's proceed further. So I think it's an empty slide. So what it means is I need to summarize the three input NAND gates and how did we estimate the delay of the three input NAND gate. So this is the three input NAND gate. So I'm going to summarize this again. So again we have the pull up circuit for the three input NAND gate to be in parallel. All the PMOS transistors will be in parallel. So this is my PMOS transistors shown with a bubbled sign, bubbled input that represents our PMOS transistors. And then, so three of the NMOS transistors will be in series in the three input NAND gate, and this will be our the output node. Just to make the inputs A and A here, and then the B input, and then the C input, and then similarly I'm going to represent the B and the C inputs on the pull down side, so B and C. What should be the sizing? As per our as per our understanding, we need the rising resistance equal to that of the rising resistance of the unit inverter. So the unit inverter I'm going to draw the PMOS and NMOS tied inputs, and then this will be my VDD, and then this will be ground. And for the inverter, unit inverter, we need a size of 2:1 so as to give get us the resistance equivalent to R, and then the resistance here equivalent to R. So in a similar way, if I want a rising resistance and then a falling resistance equal to R here and then the R here, the sizing of this particular three input NAND gate should be 3, 3 and 3, and then here in the worst case condition, one of the transistors will be on, one of the PMOS transistors will be on, and the other two will be off, and making this as the size as 2 and 2 and 2. Right. So what we are seeing is a PMOS and NMOS size ratio for a three input NAND gate NMOS is nothing but 2:3. Right. So this is what we are going to represent from here on, 2:3 for a three input NAND gate, and 2:1 for a an inverter gate. And also we had estimated the delay by utilizing the capacitance, or by expressing the capacitance at the output node and at the inter diffusion nodes as well. So at the output side, I'm going to represent an equivalent or an accumulated capacitances coming from the diffusions of the transistor A, B and C from the PMOS side, and then from the transistor A on the NMOS side. So overall, I'll get 2 plus 2 plus 2 plus 3, which will be around 9 C capacitance at the output node. The internode diffusion capacitance will give me a capacitance of 3 here because of the merged uncontacted diffusion nodes. And then here also we will get a capacitance of 3. All right, so this is about the 3 input NAND gate as a standalone gates. I'm going to see a capacitance of 9C. Now, if I make this output node, this particular output node fed to another, 3 input NAND gates or multiple 3 input NAND gates. So what what I am visualizing is, the first stage is a 3 input NAND gate. The second stage, the output of the first stage is fed to the second stage inputs of one such 3 input NAND gate or multiple such 3 input NAND gates in the second stage. So remember that when I connect this to the next stage, the input capacitance of the next stage will be considered as a load capacitance for the first stage. So the load capacitance for the first stage will be nothing but its own parasitic capacitance of 9C plus the input capacitance coming from the next stage. If I'm connecting this 3 input NAND gate to another 3 input NAND gate of the similar dimensions, the input of the second stage, the input of the second stage 3 input NAND gate will be nothing but 3 plus 2, because that's the input. So each of these inputs sees a capacitance of phi c, right? So the B also gets a capacitance of phi c, and C also sees a capacitance of phi c. So if I'm connecting this output to the next stage of a 3-input NAND gate, again I should get additional phi c capacitance added or considered in the load capacitance for the first stage. Right? Hope this is clear. And moving on. So that is what we have here in this particular slide. I'm talking about a 3-input NAND gate driving H identical NAND gates. And what do you mean by the H identical? That means the size of the second stage NAND gates are same. So it is basically something like this. The first stage, you have a 3-input NAND gate, and which is then fed to H such 3-input NAND gate. 3-input NAND gate. Right, so the number of the 3-input NAND gate is nothing but H. Right, so in that case, each of this 3-input NAND gate, is going to give me a capacitance of phi c. Each of this 3-input NAND gate is going to give capacitance of phi c, So H number of times will give me phi c H. 9C is its own parasitic capacitance. Parasitics or the diffusion capacitance, or also we can call it as the depletion capacitance. So 9C plus phi c into H will now be considered across the output node. Its own internode diffusion capacitance, or also called as merged uncontacted diffusion capacitance, is 3C, and then 3C here. And I've drawn it only for the pull down circuit because I'm considering only the falling output at this particular stage, and I want to estimate what is the falling output, the propagation delay for the falling output. So this is what the propagation delay falling out for the falling output turns out to be nothing but you will use one can use the Elmore delay method and then estimate what is the propagation delay for the falling output. So this particular the transistor C, which is closest to the source, is going to contribute to a switching resistance of R by 3. The B transistor is going to contribute R by 3, and then the A transistor is going to contribute a resistance of R by 3. Right, so I will have this particular capacitance multiplied by R by 3. Right, so that is this particular term. Right, and then this particular capacitance multiplied by R by 3 and R by 3 connected to the source, which is nothing but ground. So 3C multiplied by 2R by 3. And then finally 9C plus phi c into H multiplied by R by 3, R by 3 and R by 3, which will give me a equivalent value of R. So we will get the propagation delay falling for a 3-input NAND gate driving H identical NAND gates will be nothing but, this is 9R, and then this is 1R, and this is 2R. So finally I will get 12RC plus phi H RC. Right. Earlier, when it was not connected to the H identical NAND gates, we got the propagation delay falling as 12RC. Right. If it is now connected to H number of 3-input NAND gates, each of the NAND gates incorporates a capacitance of phi c, and that's why we are saying phi H into RC. Right. Hope this is clear. Moving forward, what is the propagation delay for the rising output for the same configuration? So the 3-input NAND gate driving the H identical NAND gates for the rising output. Again, we will consider the worst case condition. So the worst case condition is one of the transistor is on, the other two will be off. And nevertheless, on top of it, we have on the pull down side, the two transistors which are away from the ground. The two transistors A and B, which are away from the ground because C is closer to the ground rail. So the two transistors which are away from the ground and then closer to the output node are on. So the worst case condition, I will have this 3C capacitance and this 3C capacitance also to be considered in our delay estimation, thereby increasing our delay and thereby giving the worst case delay. So in such a scenario, when these two transistors are on the PMOS, on the pull down side, on the NMOS transistor, that means on the PMOS side, the A and B transistors will be off. and C is only on. So that means C is 0 here. That means that the C will be 0 here represents that the C transistors on the NMOS side is off. So now I'm left with 3 such capacitance. One is a 9C plus 5HC because this output node is connected to H such 3 input NAND gate on the second stage. So I'm having 9C plus 5HC, and then I'm having this 3C and then this 3C capacitance. So using again the NOR delay method, I should be able to find out the propagation delay rising, which will be nothing but 9C plus 5HC into R. For this 3C capacitance also, the shared resistance is nothing but this particular resistance, which is nothing but R. Again, for this 3C capacitance, the shared resistance is nothing but R. So finally, I will get 3C plus 3C multiplied by R plus 9C, which will be 15 RC, and then the additional 5H RC. When we considered the rising delay for a 3-input NAND gate without the H-identical NAND gates, without cascading to the next stage, we got 15 RC as the rising delay. Right here, because of the 5HC parameter, we are getting 5HC into R for the rising delay. That's an additional, coming from the next stage capacitance. So that is going to add to the delay. All right, hope this is clear. So what we have seen up till now is the falling delay and then the rising delay for the 2 stages, where the first stage is a 3-input NAND gate, and then the second stage is the H-identical NAND gates. So in this particular slide, we are going to look at the contamination delay for the 3-input NAND gate, and again we will look into the falling, the falling output. So the contamination delay for the falling and the contamination delay for the rising output. So let's take a look at the for the falling output. So what we really want is the input. Let's say that it starts from 0, 1, 1. And then changes to 1, 1, 0. All right. For a 3-input NAND gate. So if it is, if I'm going to write it as ABC here, and then this is what the ABC represents. The output for both the states for a 3-input NAND gate, this is 0. That means the PMOS transistor is on, and then the output will be charged to VDD. In this case also the output should be charged to VDD because one of the transistor is on and the PMOS side, and on respectively on the NMOS side one of the transistor is off. That means that the output node cannot discharge, it can only charge to VDD. So the output should be Y here, Y is equal to 1, and then Y should be equal to 1 here. But for some reason the input, when it does the transition, for example, if I take this A input, right, if this A input, it does the transition from 0 to 1, right? B doesn't change at all, so there is no transition for B, and there is a transition for C, 1 to 0. So let's say that for whatever reason, not all the inputs does the transition at the same time. So it is quite possible that A will do the transition from 0 to 1 earlier than that of the C. Right, so that means that at time t is equal to 10 nanoseconds or 10 picoseconds, we will have the input A doing the transition from 0 to 1, right? But after 10 more picoseconds, the C will do the transition from 1 to 0. So in between that 10 picoseconds, after the A has done the transition, the input parameters, the input values will be actually be A has done the transition from 0 to 1, B stays at 1, C has not done the transition, so ABC is actually 1. So what it implies is the ABC value now, which makes the output go down because now all the NMOS transistors are on and the PMOS transistor, all of them are off. That means that the output Y, which should have been retained a value of 1, is now completely discharged to 0. Right? So there is a path there for the discharging. So in that case, from 0, 1, 1 to 1, 1, 1 here, in this particular case, right, the output was 1 and then it is doing the transition to 0, which is a contaminated output. So this is something we don't want, right? So what we wanted was 0, 1, 1 input going to the next state of 1, 1, 0. That means that the output should not have been changed. It should have retained Y is equal to 1 for both the states. But because the input transition has arrived late, for one of the input transitions has arrived late, and one of them has arrived earlier. So in that case, we don't have that control, and we will get a small output glitch from 1 to 0, and then after that, once we have the C input doing the transition from 1 to 0, this Y will go from 0 to 1, right? But there is a small glitch here. So that means if I draw the Y output profile, I'll actually get 1 here, and then there will be a small glitch, and then it will go back to 1, right? So this is 0, and then this is 1, right? So this is a contaminated output, and that's why we are calling it as a contaminated delay. And especially because it's a falling output, we will call it as the falling contaminated TCDF, contamination delay for the falling output. And if I look at the schematic here and its associated capacitance, we should be able to derive at the contamination delay for the falling output. So the output capacitance is nothing but 9C, and internode diffusion capacitance is 3C and 3C. So if I have A doing the transition from 0 to 1, B is anyways 1 to 1, and then C is nothing but 1 to 1. So if I'm taking this middle state transition, A is changing from 0 to 1. So earlier it was 0, and now it is changing to 1. That means its associated capacitance here on the 9C at the output side, 9C. So there was no path here, channel path for the 9C capacitance to discharge to 0, right? So earlier when A was 0, there was no channel formed here. That means that there was no discharging path for the 9C capacitance. So the 9C capacitance was earlier charged to VDD value, and the moment A goes to 1, it should start discharging, right? Hope that is clear. B was earlier 1, and now also it is 1 in this particular intermediate state of 1, 1, 1. So that means this 3C capacitance earlier when the B was 1 here, right, this particular 3C capacitance, right, would have completely discharged. C was also 1. In this case, C is 1 here, and then C is 1 here, right? So C, the earlier 1. So there was a, the channel was formed in this particular C transistor, and thereby we get this particular, this particular channel is also formed, this particular channel is also formed. So the discharging path for both this capacitance was earlier available, and it would have completely discharged to 0, right? So what it means is in the earlier state of 0, 1, 1, the capacitances are completely discharged. Right? Which capacitances? The 3C capacitor and 3C capacitances, which are nothing but, finding a discharge path through the on transistor. The on transistors are nothing but B and C on transistors. So the contamination delay is nothing but, all the delay associated with the 9C, which is the output node capacitance. So the 9C multiplied by this R by 3, this R by 3, and this R by 3 will form the discharge path or the switching resistance, and we will get 9C into R. And we will not consider this 3C here, and then we will not consider this 3C here, because it is completely discharged to 0. Right? The moment the output, at this particular stage itself, 0, 1, 1, both these capacitances, 3C and 3C capacitances, are discharged to 0. So the only capacitance that has to discharge to 0 to give us output of 0 here will be this 9C capacitance, and thereby it is called as, so that's why the delay is associated with this particular 9C capacitance and not with this 3C and 3C. But since this output 0 is a contaminated output, that's why we call it as a contamination delay for the following. Turns out to be 9RC. If at all this output was cascaded to the next stage with 5H C capacitances, seen as the load capacitances, because we have the H number of 3 input NAND gates in the next stage, then this particular value would have been 9RC plus 5H into RC. Right? Remember, just to compare with that of the propagation delay falling for the 3 input NAND gate, it is nothing but 12RC. Right? So if I am comparing the contamination delay, the propagation delay should always be higher, and contamination delay should always be the lower value. Right? And I think this contamination delay is kind of very, very, it's one of the design parameters that we need to consider especially while we designing the sequential elements. So once we have the flip-flops or the latches, and in between the combinational circuits, and then followed by one more sequential elements, we have to consider the contamination delay so that the whole the time violation doesn't happen, and the whole time violation is characterized for a particular sequential element, right? So when we talk about the sequential elements, we will once again take this particular involve this particular parameter, the contamination delay, and that's why so all of you should be able to understand the contamination delay, and that's why it is there in this particular lecture. Okay, moving forward, what should be the rising contamination delay? Right, so the rising contamination delay is, it's a very straightforward. If all of them, I want a rising output here, and for the propagation delay rising, we had always considered the worst case where one of the transistors is on, the other two will be off. For the rising one, the best case delay is nothing but when all the three transistors are on. Transistor A is on, transistor B is on, transistor C is on. And if all the three transistors are on, the equivalent switching resistance seen from the PMOS side is nothing but the switching resistance of A in parallel with switching resistance of B in parallel with that of the switching resistance of the C. Right? So the equivalent resistance will be nothing but R by 3. Right? Because each of these gates are of the size 2. This is the size 2, this is the size 2. Each one of them will offer a resistance of R each, and then 3 of them in parallel, so we'll get R by 3. And the output node capacitance is 9C, and if this is 0, and this is 0, we will not consider this 3C capacitance. We will not consider this 3C capacitance because there is no charging path. There is no path here, there is no path here, there is no, for this 3C capacitance to charge. Right, so this particular path is not there. This particular path is also not there. So the only thing which sees the path, the charging part, is the 9C capacitance. So we will have 9C into R by 3, which will give me 3RC. So that will be the rising contamination delay. Now, in our previous example of the falling contamination delay, we had taken two states, right? 0, 1, 1 to 1, 1, 0. An intermediate state was 1, 1, 1. And that's where we said that it is contaminated. It gives us a contaminated output. Here, we have not considered that, right? So here, what I'm saying is, if my state, for whatever reason, if I had 1, 1, 0 as my initial state, or rather 1, 0, 0 as my initial state, the output for 1, 0, 0 as an input. So if this is the input A, B, C as 1, 0, 0. So the output for this A, B, C of 1, 0, 0 will be nothing but 1, right? And let's say it changes to A, B, C of 0, 1, 0. The output is still 1. All right. I think this is possibly this is a kind of a bad example. So let's say that the output is the input is ABC and it is 1, 1, 1. So I will get the output to be 0, and it should have been state to 1, 1, 1. But whatever reason at the input side, at the input side of A, B, and C, if we get a lot of noise signals, then we can have the state of ABC as 0, 0, 0, where the output will now become 1, right? So this is all induced due to the input noise signal, right? But then the noise will have, it could be a very high frequency or something. So we will see a kind of a glitch here, the input doing the transition from 1, 1, 1 to 0, 0, 0 in a very, very small time duration, and then get back to 1, 1, 1, right? In that case, my output will be 0 throughout, but then there will be a glitch of 1, and then it will come down to 0. Right? So that is where, the contamination delay could be due to the problems at the input side. Input transition doesn't, for if I have a multiple inputs, the inputs doesn't do the transition at the same time. So that is one reason. Another reason could be the input noise signal, which can change the logic level at the input side, and thereby the output state also changes, right? And it all happens momentarily. So it is not there as a steady state. So you will see the glitch, and then for the next steady state input, you should get an steady state output, right? So all this are momentary output changes, and that is where we are considering the contamination delay, because all these glitches are contaminated outputs, right? Hope you understood this. So here we are revisiting the 3-input NAND gate driving the H identical NAND gates. So this is something we had already seen. So sizes of the 3 and 3 are written, and on the PMOS side, the size is nothing but 2 for each of the PMOS transistors. I'm considering only the falling output. That's why I've taken only the pull down circuit. That means only the NMOS transistors is in the picture. We have drawn the output node capacitance, and then this is coming from the next stage, so phi C into H, because H identical NAND gates are there in the second stage. So this output is actually fed to the H identical NAND gates, and 9C is coming from its own parasitic capacitance, right? So overall propagation delay falling is nothing but 12 RC plus phi H RC. Right, which is something we had seen earlier in one of the previous slides. This 12 RC is actually, if I consider this 12 RC, it is actually coming from this 9C. It's actually coming from this 3C. This is actually coming from this 3C, right? And then this phi HC is going to give me phi HRC, right, which is coming from the next stage input. And then this 12 RC is its own parasitic. So all these capacitances, 9C, 3C, and then 3C are its own diffusion or parasitic capacitances. So that's why this particular component, if I actually segment it to the two components, 12 RC and phi HRC, first component is the parasitic delay because it is coming from the parasitic capacitances. The second component, which is coming from the second stage, input capacitances, is we are calling it as an effort delay. So this is an additional effort in terms of delay. This particular, the first stage circuit is doing with respect to the for the next stage, right? So it could be the next stage could be no circuit at all. So in that case, there is no effort. So there is no effort delay. But if I have in the second stage there is some circuit, so I'll have to put some effort in the delay. So my performance or the delay will be larger. So that's why this is called as an effort delay. So the first stage is putting an effort for the second stage. This could also be represented as P plus GH. What it really means is the parasitic delay component and then the effort delay called as G into H. So each of this is now a value, right, or an expression. So P is parasitic delay, G is something, and then H is something. H is something we have also called earlier as an electrical effort or a fan out, right? And then G, we will call it as a logical effort. So all these are the parameters for a design circuit. The design circuit could be a 3-input NAND gate, 2-input NAND gate, 3-input NOR gate, inverter, and then so on, and even the combinational circuits, right? And I've stated here as the normalized. So generally, when I get the delay parameters for a 3-input, for a 3-input NAND gate or any other circuit, so I'll get the propagation delay falling or rising. Generally, we normalize it with respect to the inverter's delay, right? So what it means is I need to always benchmark my circuit, my combinational circuits or whatever, the 2-input NAND gates or the 3-input combinatorial gates with respect to the inverter. So the inverter, the 2:1 inverter, which is a unit inverter, now, according to us, that is the, we know the delay parameters for that, right? It will be nothing but 3 into RC. If R and C is, 10 kilo ohms and then 0.1 femtofarads respectively, we know that will be 3 picoseconds, right? So we will always benchmark any of the combinational circuits, or in this case, a 3-input NAND gate, and its delay with respect to the 3 picoseconds, right? So in that case, what we will do is this particular propagation delay falling, the absolute value of the propagation delay falling for the 3-input NAND gate, we will try to normalize it. So normalizing with respect to the 2:1 inverter. So what we will do is for normalizing, if we want a normalized delay component, it will be nothing but this particular expression divided by 3RC. So finally, we should be able to get the normalized component is nothing but 4 plus 5 by 3. Right? So I'll come to that later. Hope you have understood this. So the gist of this particular slide was the delay component is actually segmented into two parts. One is the parasitic component, the other one is the effort delay. Okay, before getting into P plus DH format, let's see what happens if I change the size of this particular 3-input NAND gate, right? Uniformly scale it. Right, so if I double the size of the transistors in a 3-input NAND gate, so instead of our, if you remember the PMOS and NMOS in our earlier 3-input NAND gate, right, the sizes was 2:3. That means on the NMOS side, the size was 3. On the PMOS side, the size was 2. Right, so in that case, if I double this up, so if I do 2 multiplied by 2 and then double this up on the PMOS and NMOS side, so that means I'll get a size of 4, 4 and 4 on the PMOS side and a size of 6, 6 and 6 on the NMOS side. So if I have those, my switching resistance here, so let me use a different color. My switching resistance here will be R by 2. Because it is now 4, so that means on the PMOS side, if the width is scaled by k times, it will be 2R by k. So 2R by 4 will be nothing but R by 2. Even this one will be R by 2, even this one will be R by 2. The switching resistance on the NMOS side will be nothing but R by 6. This will be R by 6 again, and then this will be R by 6. Right? And however, if I scale the transistors, if I scale the dimensions of the transistors, especially the width, my capacitance here is going to increase, right? So the diffusion capacitances or the parasitic capacitances, so if I look into this particular capacitances, it will be not be 3C, it will be 6C, K into C. This particular diffusion capacitance is going to give me 6C. The diffusion capacitances here coming from this particular transistor will be 4C. This particular capacitance will be 4C. This particular capacitance will be 4C, and I know this particular capacitance, because it is 6 size, it will be 6C. So my overall load capacitance seen at the output side for a single stage 3-input NAND gate will be nothing but this particular 6C. So let me use a different marker, 6C plus 4C plus 4C plus 4C. So it turns out to be 18C instead of a 9C capacitance, especially for, when we are using 2:3 3-input NAND gates, we had 9C. Instead of that, now it is 18C. Right? So what we have deduced is if I change the size of the transistors, if I increase the size, the capacitance, the parasitic capacitance is going to scale up, right? The switching resistance is going to scale down, right? And if I try to find out the propagation delay falling, right, I'll use the Elmore delay method for the falling. So all of them has to be 1 on the NMOS side. All the NMOS transistors should be on, then only I'll get the output node to be discharging to 0. So I'll get this 6C multiplied by R by 6. So this is the first component, 6C into R by 6. And then the next component will be 6C multiplied by 2 into R. So R by 6 plus R by 6. And the last one is the 18C multiplied by R by 6 plus R by 6 plus R by 6. So it will be 3R by 6. So overall, the propagation delay falling turns out to be the same 12RC. What we had seen was for the 2:3 3-input NAND gate also. So 2:3 ratio for that particular 3-input NAND gate also, we got the propagation delay falling as 12RC. Even for 4:6, for the 4:6, for 4 and 6 ratio, that also we got the propagation delay falling is 12RC. Right? What I've done is I've not considered the next stage. So I consider only this particular first stage, change the size accordingly, and then determine that the propagation delay falling doesn't change. Right, so that's what I've written here. It is the propagation delay falling is the same as that of the PMOS and NMOS of 2:3 size. So what we are concluding is the parasitic part of the delay, which is nothing but it's associated with its own capacitances. Now what I had said in the earlier slide, the parasitic delay and not the effort delay. Effort delay is coming from the next stage. So the parasitic delay is due to its own stage, or the own parasitic or the depletion or diffusion capacitances. That is not going to change. That remains independent of the size of the transistors.